In this screencast, we're going to focus on finding the arc length parameter, or finding derivatives with respect to s. First, recall the arc length. The arc length is found by integrating the speed with respect to t, where you've got your bounds given a to b. We're going to define a new function, calling it s of t, and rather than integrating from a to b, we're going to integrate from a to t. And then, of course, we'll integrate the speed dt. What this function does is rather than integrating from a to b, I'm going to integrate from a to t, so if you tell me the time that you've been moving along the curve, I'll be able to tell you the arc length. In the book, you'll find that it's written a to t r prime tau d tau. They just used a tau instead of a t because tau is a dummy variable of integration. This function has a derivative. The derivative of s with respect to t is found by taking the derivative of an integral. And the derivative of an integral is precisely the thing you started with. That's the fundamental theorem of calculus, that when you differentiate an integral, you get what you began with. So, key thing to note here is that the rate of change of arc length over time is speed. Speed equals distance over time. Now, we're going to apply this to a specific curve. Let's consider a helix. So r of t equals cosine t, sine t, t. And normally we start helices at 0, so that'll be our beginning spot, and then we'll just integrate to t. The derivative, or dr dt, is negative sine t, cosine t, 1. And the magnitude of that is the square root of sine squared plus cosine squared plus 1, but sine squared plus cosine squared is 1, so this is the square root of 1 plus 1, which is the square root of 2. Which means the arc length parameter, s of t, is the integral from 0 to t. We'll put the root 2 in there, dt. This is just root 2 times t, which means we get arc length is root 2 times t. If you've been traveling for 10 seconds, then you have gone 10 root 2 units. This function's invertible, and I could solve instead for t, getting an s over 2. Here is where we end up taking derivatives with respect to s instead of t. If I go back to my function r and replace every t with what it is in terms of s, then I get out cosine of s over root 2, sine of s over root 2, s over root 2. At this point, I can now go through and calculate a derivative of r with respect to arc length, rather than with respect to time. Well, that gives me a negative sine s over root 2 times 1 over root 2, and then I have a cosine s over root 2 times 1 over root 2, and then I have a 1 over root 2. That said, I now can find the length of that vector, dr ds's length, which is, pick square roots, so I get a sine squared s over root 2 times 1/2 plus a cosine squared s over root 2 times 1 over root 2, but I've got to square that, so yeah, 1 over 2, plus a 1/2. Again, I have a 1/2 times a sine squared plus cosine squared, so that ends up being a half plus a half, which ends up just being the square root of 1, or 1. So what that means is dr ds is a unit vector. Its length is 1. So that means dr ds is our unit tangent vector. And that completes the screen.